I am back to my office here at Central Paris, and it is a pleasure to hold these office hours today. Again, I will talk about separability, and there was a question in the forum that I will address. Separability of a space X means that you can find a subset Y which is dense in X and which is countable. Now, Y dense in X means that you can approximate any element of X by an element of Y. If you have a metric space, what it really means is that for any element of X and for any epsilon, which is not zero, positive, you can find an element in Y for which the distance to X is smaller than epsilon. That's why I'm saying you can approximate any element of X by an element of Y, provided you give yourself an accuracy epsilon that you don't want the distance to be greater than that. In addition to being dense, you also ask Y to be countable. And as you know, countable means that you have the same number of elements as n, the set of integers, so to speak. Of course, there are an infinite number of elements, but there are different types of infinity. And as you know, countable means this kind of infinity is the same as the kind of infinity to n. So n is countable, q, the set of rational numbers, is countable, but r, the real line, the set of real numbers, is not countable. So here is separability. You have a dense, countable subspace of the set. LP spaces will be separable when P is in between 1 included and plus infinity excluded. And L infinity will not be separable. This is what we saw in the lecture. But the proof for the separability of LP spaces where P is not plus infinity relies on the fact that the set of continuous functions with compact support, C0C, is dense in LP and itself is separable, which means I can approximate my functions in C0C by functions that I can find in a set which is countable. And the set which is countable, with whom I approximate my continuous function with compact support, the set of this set which is countable is simply given by piecewise constant functions, and I need to make sure that the n's are rational numbers, so this actually will be a set of countable functions. So that's the idea for separability for LP spaces. First, I prove separability for C0C, and then the fact that C0C is dense in LP yields the proof. Now here's the proof that L infinity is not separable. And I define Rx and Ox, and what I will do is give you an example so you can understand better what we're doing here. Let me give you an example for n equals to 1, and the open set omega will be the interval 0, 1. Now, let me give you an example for x equals, say, 0.8. So if x is equal to 0.8, the r of 0.8, r of 0.8, will be the distance to the boundary, basically, of the interval, so that will be 0.2. And the function 1, index b of 0.8, 0.2, which is the distance to the boundary, will simply be this function which is 0, and then starting at 0.6, it will be 1 all the way to 1. So this is the function 1, index b of 0.8, r of 0.8, and again, r of 0.8 is 0.2. Now the set O, index 0.8, will be the set of all functions in L infinity for which the distance between this function and that function 1, index b 0.8, 0.2 is smaller than 1/2. So what we're doing here is saying that the set O, index 0.8, is the set of functions f that can take any value in between negative 1/2 and 1/2 in between 0 and 0.6, and they have to take a value in between 0.5 and 1.5, in between 0.6 and 1. So you see this function OX. Now, so that was O index 0.8. Now, if you look at O index 0.9, then you can see what it is. O index 0.9 will be the functions f that are in L infinity, for which that have to be in between -1/2 and 1/2, between 0 and 0.8 this time, and that have to be in between 0.5 and 1.5 from 0.8 to 1. So you can see that now if you look at O index 0.8 and O index 0.9, you can see that these functions will have no elements in common. Right? You cannot be at the same time in between -1/2 and 1/2 strictly, and between 1/2 and 3/2 strictly. Right? So what happens is that in between 0.6 and 0.8, you've got a problem. You cannot be at the same time in O 0.8 and in O 0.9. So what I'm saying is that the intersection of OX and OY will be the empty set if X is different from Y. And there was a typo in the original slide, which has been corrected here on the slide, which is here appearing on the screen. So that's important. OX intersected with OY is the empty set if X is different from Y. And from there, then we can actually do the rest of the proof, which is suppose there exists a dense sequence UN L infinity, and then what we have is get a contradiction. So what we have is that basically such a dense sequence cannot exist in L infinity, which yields the fact that L infinity is not separable. This is the end of our office hours today from Paris, France. Before we break, I would like to tell you a joke about countability, countable number of elements, and actually countable number of rooms. It's called the Hilbert Hotel, even though the joke is not from Hilbert himself. So we have a Hilbert Hotel, which is a hotel with an infinite countable number of rooms. Now this hotel is full, which means there is a guest in every room. And we have a new guest that shows up at the front desk, and the receptionist is really sad because there is no room for this new guest. So he was about to turn him away when Hilbert shows up and says, well, no, let's actually accept this guest. All you need to do is to ask people who are in room N to go to room N+1. And that will free up the first room of the hotel, and so we can accommodate the guest. And if you think about it, what it means is that n and n star, the set of integers n, and the set of integers without 0, n star, can actually be put in bijection. There is a one-to-one mapping. And so that's two good news. The first one is that n star and n are countable. The other good news is that this guest could actually get some rest at the hotel. And then the next day there is a countable infinite number of guests who show up at the hotel. So what I would like you to think about is what you would do if you have a countable number of guests showing up at the hotel, which has a countable number of rooms, but all of them are actually used. The hotel is full. What would you do? And I suggest you think about it, and we will give the answer next week in these office hours. In between now and then, I wish you a wonderful week, and I see you soon.